differentiability, which is just a fancy word, whether or not a function is differentiable. So when we differentiate functions, in order for it to work, the curve has to be what we call smooth continuous. Okay? So in other words, if we use an idea of limits and approach it from left to right, but this time instead of looking at the function value, we're looking at the value of the derivative itself. But again, the derivative as we approach it from the left-hand side has to be the same as when we approach it from the right-hand side. So if I have this absolute value curve, which is continuous, there's no question about that, but it's not smooth continuous. It's got a sharp point, which means, look, at x equals 1, this curve is not differentiable, because how do you draw a tangent at that sharp point? Where would you put the tangent? Because if we come from the left-hand side, we'd have a slope of -1, but if we come from the right-hand side, we have a slope of positive. So because those values are different, so if I didn't actually have the picture, I could look at the value and go, oh, no, well, that's not differentiable. Whereas, say, our parabola, our standard parabola, if I was to as one as well, same point, there is only one tangent I could draw at 1, and whether I come at it from the left-hand side or the right-hand side, it's still going to be the same tangent. So it is differentiable at 1. All you really need to know is it's got to be smooth continuous. The only thing they'd ever ask you is, they might give you a picture of a graph and say, where is this not differentiable? And you go, oh, look, there's a sharp point there, so that one's not. Or it's discontinuous there, so that one. So they won't ask for a formal definition or anything on that. If they do happen to ask it, it's a very rare question, but if they do happen to mention differentiability, that's basically what we're looking for. It's got to be smooth and continuous. All right, we're going to finish off with this idea of implicit differentiation, which is something we have already seen under another name. Now, technically, implicit differentiation is in the Extension 2 course. But as I say, we have already seen it under another name. Because that's all it is. So there it is again, rates of change, chain rule, call it whatever you like. It's that idea of we can build a derivative using other derivatives. The reason it's called implicit differentiation, all the differentiation we've been doing so far is explicit differentiation, because we made y the subject. So it's explicitly y is equal to this, and we went and differentiated. So this would be an explicit one. But the idea is simply, as I was mentioning before, it's just an equation. Whatever you do to one side, you do to the other. So theoretically, I'll differentiate y with respect to x. Well, hang on, I can't differentiate y with respect to x. So what I'm really doing, and this is where implicit differentiation comes in, I can't differentiate y with respect to x, but I can differentiate it with respect to y. So if I do that, but in order to balance it out, I would then have to multiply by dy dx. The dy's cancel if you like, and I get the derivative with respect to x. On the right-hand side, I can do that one with respect to x. Differentiate y with respect to y, and of course we get 1. So it's 1 times dy dx is 2x, and there we go, dy dx is 2x. Now, of course, you wrote it in one line, but that really is the mechanics behind it of how we get there. If we use that idea, we can now apply that same idea to now something implicit like x equals y squared, a parabola on its side. Now, yes, I could rearrange this and make y the subject, but instead of doing that, I'm still going to use the same idea. I'm going to differentiate both sides with respect to x. So on the left-hand side, I'll differentiate x with respect to x. On the right-hand side, I'll differentiate y squared with respect to x. Hang on, I can't differentiate it with respect to x, but I can differentiate it with respect to y. So when I differentiate y squared with respect to x, what I really do is I differentiate it with respect to y and then multiply it by dy dx to balance it out. So I end up with, on the left-hand side, differentiate x with respect to x, I get 1. Differentiate the y squared, well, with respect to y, that would be 2y, but I multiply it by dy dx. I'll make dy dx the subject. there's my derivative. It's just in terms of y instead of x. So instead of substituting in the x value, I'll substitute in the y value. Now, there's a reason why we do that, because if you think about what the shape is, it's a parabola on its side. So if I use the x value, well, it's not a function. So there's two possible answers, depending on which point I'm talking about. Because parabola on the side, however, if I use the y value, now I only get one possible answer. And so it actually makes more sense to use a y value for one like that, and you get 1 on 2y. So again, if we take it a step further, say I end up with something, combination of x and y's. Obviously this one's not an equation, but I'm just saying, hey, if we had to differentiate this term, I've got x squared times y cubed. Well, I would use a product rule. Write down the first, x squared. Diff the second. Okay, I'm going to differentiate y cubed, but I can't do that with respect to x. I'll do it with respect to y. So differentiate y cubed, I get 3y squared times dy dx. Plus, write down the second, y cubed. Diff the first, I get 2x. And so that would be my derivative of x squared, y cubed. 3x squared y squared times dy dx plus 2x y cubed. It's a strange looking derivative, but that's what it is. Now to the point I was finally getting to. So if you've got a circle and you want to find the equation of a tangent at a circle. Now, of course, a circle is not a function. I could make y the subject and then work out, oh, hang on, do I want the positive square root or do I want the negative square root? But rather than do it explicitly, it's easier to do it implicitly. So I've got x squared plus y squared equals 9. I'm just going to differentiate both sides with respect to x. Well, differentiate x squared, that's not a problem, 2x. Differentiate y squared, can't do it with respect to x, but I can do it with respect to y. So I differentiate with respect to y, 2y, but then to balance it out, I need to multiply it by dy dx. Right hand side, differentiate a constant, and of course I get 0. If I make dy dx the subject of this one, eventually, and so in order to work out the slope of the tangent for this one, I need to substitute in both the x and the y value. Again, that makes sense if you think of the shape. Because for a circle, if you pick an x value, there's two possible y values. If you pick a y value, there's two possible x values. So I need both the x and the y value to isolate, okay, which tangent am I talking about? So if I want to find this tangent, it's the point 1, 2 root 2, so if I substitute in 1 for x and 2 root 2 for y, I've got the slope of the tangent at that particular point, and now it becomes our standard question, point slope formula, play around with it, there it is in general form, x plus 2 root 2y minus 9 equals 0. Now, where this idea will come in very useful in extension 2, and I guess why they make it a part of an extension 2, is when we look at a topic of conics. We'll look at ellipses and hyperbolas and all those sorts of shapes and have to find tangents. So, handful of questions there. As I say, technically it's in the Extension 2 course, but that's not to say you can't use the idea if you see a place to use it.